Okay, so welcome back. Yeah, as I was saying, it was luckily I didn't get too sick. Really, I probably got less sick than I would with like a normal case of bronchitis or something. The problem is that um, I was coughing a ton and my voice was all messed up. So I don't think it would have done anyone any good to hear me trying to struggle through lecturing. You probably wouldn't have been able to get anything I was saying. I guess I could have just written out everything and taken like triple the time to lecture or something. But I thought it would be better, um, you know, to just wait. So because we are technically a couple lectures behind. Um, I may need to, as we get closer, probably as we get like halfway through chapter 6, I will determine whether or not I need to post like a supplemental lecture. I've thought, and probably what I'll do is if I need to post a supplemental lecture, like one or two supplemental lectures, I'll do it over Thanksgiving. And you can just watch it whenever you want to, and that way we can take care of that, in a convenient way. And I don't have to jam like, 3 lectures over a weekend or something. I think it's a lot easier that way. So anyway, in discussion yesterday, you already did some of the stuff that I'm going to cover now and that I had hinted at last time. So what is the thing that we're doing? Our main application of eigenvalues and eigenvectors is diagonalization, right? So our main application in this course for eigenvalues and eigenvectors, this entire analysis that we've been doing is diagonalization. So just to refresh your memory from the lecture that I'd posted last, so a matrix is diagonalizable if it's similar. Recall, being similar means being conjugate to. It means there exists an invertible matrix such that A is P, B, P inverse. Okay, but in this case, a matrix is diagonalizable if it's similar to a diagonal matrix D. So D is a diagonal matrix, meaning that the only non-zero entries for D possibly are on the diagonal. So I should note here that the zero matrix is itself a diagonal matrix. So these D's don't all have to be non-zero. In fact, they could all be zero. The diagonal matrix is defined in a negative way. It's defined in a way that all of the off-diagonal entries are zero. Everything else, it doesn't matter what they are. The idea here being that, typically what you have here are you have a bunch of non-zero things on the diagonal and zeros everywhere else. So anyway, if A is similar to diagonal matrix D, then there exists an invertible P such that A is, P D P inverse. So this is what it means for A to be diagonalizable. The reason why this is important is if we were dealing with a diagonalizable matrix, then this question that we originally had where we wanted to, starting with some generic matrix A, we wanted to compute A to the K, right, for some arbitrary power of this matrix. But this is hard, right? This is a difficult thing to compute. But if A were diagonal, this would be easy, right, as we've already seen. In fact, to exponentiate a diagonal matrix like this, you just raise the diagonal entries to that power and you're done. So that's obviously really easy. But A to the K in general is hard. But if A is diagonalizable, there exists a P and a diagonal matrix D such that A is P dP inverse. And then if I raise A to powers, what do I get, right? So A squared, we saw it works out that the P and P inverse cancel. So what I get here is P D squared P inverse. And similarly, raising A to any power, A to the K is P D to the K P inverse if A is diagonalizable. And so this A to the K is really, really easy to compute if A is diagonalizable. Okay. Now, So this finally ties us into exactly what I was talking about the first day we mentioned eigenvalues and eigenvectors. It's that eigenvalues and eigenvectors allow you to explain how these matrix iterates behave. Okay, which is important for varying processes, that are modeled by iterated matrix multiplication. So all of the applications in this textbook, basically, where you use iterated matrix multiplication to get you to the next time step, right? This is understanding the eigenvalues of the matrix is key to understanding what's going on here. And so, what is the deal? Well, diagonalization, it has a special name, meaning that, already you can figure out that not every matrix is diagonalizable. And the reason why you know that is mathematicians are good and efficient when it comes to their terminology. If it turned out that every matrix was diagonalizable, well, then we wouldn't have a special name for it, right? It would just be a property of every matrix. But it is the case that it is a special thing here. So someone asked in chat, the TA had it set up so that A is equal to P inverse dP. Okay, so this doesn't affect whether you have it written like this or and sometimes I flip these too. And okay, so whether you have it written like this or like this doesn't matter conceptually. It doesn't matter conceptually what's going on. Both of these are equivalent in that sense, in that whether you have either one of these, A is diagonalizable. The reason why you should list it like this is because in the process that we're going to describe, the matrix P that we get, you would need to flip everything and replace it with its inverse here. So the matrix that you would get here would not be the same P. It would be P inverse that you're describing, which is fine. But when you write this out, you're basically, if you wrote down the P that we're going to write down, but then you wrote P inverse dP, it would technically be wrong. You basically have written the inverse statement instead. So that's something to be. I'll stress that when we do some examples here in a second. And so to diagonalize and how diagonalization is related to eigenvalues and eigenvectors, this comes from what's called the diagonalization theorem. So the diagonalization theorem is the main thing here, but I'll say that we need some theorems that come later to fully describe what's going on in all the cases, because it is tricky. What's going on is a little bit tricky for a generic matrix. So there are some cases where you're going to be able to immediately see the matrix is diagonalizable. And it doesn't really have anything to do with the size of the matrix, as we'll see. It has to do with the eigenvalues. Okay, so you could have a 10 by 10 matrix, but if you have a 10 by 10 matrix that has all distinct eigenvalues, you can immediately say something about it. Versus even a 3 by 3 with repeated eigenvalues, you can't say anything immediately. So this is the diagonalization theorem. So what does the diagonalization theorem say? A matrix A that's an n by n matrix is diagonalizable if and only if, so exactly when, A has n linearly independent eigenvectors. So that is the condition, and that is simple enough. Unfortunately, if I give you a list of the eigenvalues for A, can you immediately say whether or not A satisfies this? No, not in general. That's the problem. And so actually showing that a matrix has n linearly independent eigenvectors can be tricky. That's where really like 95% of the work comes in here. Okay, so in fact, this describes the actual process for doing the diagonalization. So in fact, A is equal to P d P inverse, with D a diagonal matrix, if and only if the columns of P are n linearly independent eigenvectors of A. And in this case, the diagonal entries of D are the eigenvalues of A. I'm going to say corresponding, and it'll become clear what that means once we've done a couple of examples. So these are the corresponding eigenvalues of A. The corresponding here refers to the position of the columns of P. So the idea here is that, these in linearly independent eigenvectors, I could put them in any order I want to. So whatever order I've put them in P, the eigenvalues arranged in D have to be arranged in the same way that corresponds to that order. Okay. All right. Okay, so both of these statements are extremely important. This is, in fact, this is it. I mean, this tells you exactly what's going on. Now, unfortunately, as I said, for practical matters, how do you actually show that a matrix has n linearly independent eigenvectors? I mean, the worst thing that you would have to do is you find n eigenvectors, if they exist, and then show that they're linearly independent. Okay, well, I mean, how would you go about doing this in a shorter way? Well, we'll see how this works. Okay. All right, and so this is the diagonalization theorem. So just to recap, it's diagonalizable if and only if A has n linearly independent eigenvectors. In this case, where A is diagonalizable, so you can write it as P d P inverse, then the P is actually, the columns of P are the n linearly independent eigenvectors of A in some order, and the diagonal matrix D that A is similar to is the diagonal matrix that has the eigenvalues of A showing up on its diagonal. And the order, of course, is determined by whatever order you've put the eigenvectors in P. Okay. All right. In this case, this list of n linearly independent eigenvectors we would call an eigenvector basis of Rn. Okay, so we call that an eigenvector basis of Rn. Okay. And so let's see how we would handle this in an example. Okay. So how would an example like this go? So let's diagonalize the following matrix if possible. All right, so my matrix, reading row-wise, this is 1, 3, 3, minus 3, minus 5, minus 3, 3, 3, 1. So diagonalize this if possible. Okay, spoiler alert, it's not always possible to diagonalize a matrix. We'll see specific examples of what has to go wrong. And you might already be guessing what has to go wrong just from some of the other things that or some of the previous things we've said. So the hint here, if you want to think about this while we're doing this example, the hint here is it has something to do with the dimension of the eigenspaces. Okay, so it has something to do with the dimension of the eigenspaces, as we'll see. Okay, so first, I want to find, ideally, I'm looking to write this A as PDP inverse, right, where P is invertible and D is a diagonal matrix. Okay, so how do I do this? To diagonalize this, I need to find the eigenvalues for A first. And so, what are my eigenvalues for A? Well, let's write out the characteristic polynomial. So characteristic polynomial is what? So this is the determinant of, so my piece of A of lambda is determinant of A minus lambda I. What is A minus lambda I? Well, let's just quickly compute here. So A minus lambda I is 1 minus lambda 3, 3, minus 3, minus 5 minus lambda minus 3, 3, 3, and 1 minus lambda. Okay. If I'm computing the determinant of this thing, then, there's multiple ways that I could go about this. I'm going to suppose that I've done this already, so just to save myself some time. So it turns out that if you compute this determinant, you're going to get minus lambda cubed minus 3 lambda squared plus 4, which does factor. It's a cubic that does factor. This is minus lambda minus 1 times lambda plus 2 squared. Okay. All right. Okay. So you can do this the brute force way and see that this is exactly what you get, but I'm going to save some time here so I can get to more examples. And so what are my eigenvalues? So my eigenvalues are lambda equals 1 and minus 2. Okay. Okay. And so I'm going to, even though I haven't gotten to this yet, I think it's good to go ahead and mention this. So what is the multiplicity? What are the multiplicities of these eigenvalues? And again, in this course, to stress this, in this course, when I say multiplicity, I mean multiplicity of lambda as a root of the characteristic polynomial. Sometimes, and if you're looking this up in some, if you're learning about eigenvalues, eigenvectors, and diagonalization from some other source, there's two types of multiplicity that people talk about. There's geometric multiplicity and there's algebraic multiplicity. So what I'm saying is algebraic multiplicity. Geometric multiplicity is the dimension that I'm interested in later, but I'm not going to call it that. But this is just a warning that if you look this up, you might get a little bit confused because other textbooks like to use the term multiplicity to also mean that. So here, what I mean by multiplicity is just I fully factored the characteristic polynomial. What multiplicity does this root have? So the multiplicity of the first eigenvalue is 1. Multiplicity of minus 2 is 2. Right? Exactly. Yeah. So someone said it in chat as well. So 1 has multiplicity 1 and minus 2 has multiplicity 2. Okay. And again, this is just from the fully factored form of the characteristic polynomial. Right? So minus 2 is a double root. That's all that's being said here. Okay. Now, So this is the first step. So first step is to find eigenvalues. Second step is to find associated eigenvectors. So I need to find all associated eigenvectors, and hopefully I have found enough in this step to find 3 linearly independent eigenvectors. Okay, so in order to do this, what I'm really looking for is I'm looking at, the null space of A minus lambda equals 1 I, and I'm looking at the null space of A plus 2 I, right? This is what I'm looking for. So this is the lambda equals minus 2 eigenspace, right? And this is the lambda equals 1 eigenspace. Okay. So looking at these two eigenspaces, I'm finding bases here. So what is a basis for the lambda equals 1 eigenspace? Well, it turns out, and again, I'm not going to go through this, but it turns out that here's a basis. It is one-dimensional. It is the single vector 1 minus 1, 1. Now, I'm not going to say anything more here, but I'm going to say when you have a simple eigenvalue. A simple eigenvalue is an eigenvalue that has multiplicity 1. When you have a simple eigenvalue, you know that the dimension of the eigenspace is 1. Okay. All right. Here, I don't have a simple eigenvalue. I have eigenvalue that has multiplicity 2. Do I know inherently that the dimension of the associated eigenspace is 2? The answer is no. I don't know that. And this is exactly the problem here. Okay, this is exactly the thing that can go wrong with diagonalization. So in this case, it turns out that a basis, so here was my basis for my lambda equals 1 eigenspace. My basis for the lambda equals 2 eigenspace comes from the two vectors that I'll label v2 and v3. So it is consists of these two vectors, v2 and v3. So that's minus 1, 1, 0, and minus 1, 0, 1. Okay. And so the linearly independent set that I'm looking for is just the one that consists of these three vectors. Okay. Now, how do I construct P? So now let's, so our third step here is construct P. How do I construct P? Well, P is just those, its columns are those linearly independent eigenvectors. So I'm going to put them in this order. V1, V2, V3. Did I have to? No. And we'll see how this changes my answer here in a second. So, writing this out, right, using the same V1, V2, and V3 from before. So I'm now reading column-wise. So V1 is 1, minus 1, 1. V2 is minus 1, 1, 0. And V3 is minus 1, 0, 1. Okay, so there's my matrix P. And now I construct D. So here is all this crap I've been mentioning about how to construct D in a way that corresponds to P. The idea is we know that D is diagonal. Okay, so D is a diagonal 3 by 3 matrix. So it looks like this, with stuff on the diagonals. Now, to make sure that if I want A to be P, D, P inverse, if this is my P, so this is eigenvector associated to lambda equals 1, and these two eigenvectors were associated to lambda equals 2, right? Just to remind you. V1 was associated to the lambda equals 1 eigenspace. V2 and V3 were the bases of They were the basis vectors of the lambda equals minus 2 eigenspace. So V2 and V3 are associated to lambda equals minus 2, and V1 is associated to lambda equals 1, right? You can write that here, right? So this is lambda equals 1. This is associated to lambda equals minus 2. This is associated to lambda equals minus 2. And so when I write this D in this order, it would be 1, minus 2, minus 2. Okay. So note, D is diagonal matrix. It contains the eigenvalues of A on it, and the number of times that an eigenvalue shows up is the multiplicity of that eigenvalue as a root of the characteristic polynomial. So here are my eigenvalues for A, 1 and minus 2. 1 had multiplicity 1, minus 2 had multiplicity 2. So minus 2 shows up twice here, 1 shows up once. Okay. Now, to show you how this would change if I had arranged this differently. Let's say for whatever reason I did this in a different way. So let's say, so forget this for a second. Let's say that I said let P be, because I don't care here. Let's say let P be V2, V3, V1. Right? I could have done that. So here's my P. It's reading column wise. This is minus 1, 1, 0, minus 1, 0, 1, and 1, minus 1, 1. Is that fine for your P? Yep, that's fine. A is still equal to P dP inverse. But now D has to change to accommodate it, and it would have to change to be minus 2, 1, right, instead. So this is what I meant by the diagonal entries for D correspond to the eigenvectors in P in this way. Well, a little bit off screen. All right. And so this is how P and D would change to accommodate one another. So you can actually check, I'm not going to, but you can actually check if you want to see that this actually worked here. Rather than finding P inverse and all that stuff, to check A equals P dP inverse, what you could do instead is multiply on the right by P. You're really checking that A times P is equal to P times D. This way you don't have to find the inverse of P, and you can actually check that, oh, indeed, A times P and P times D are the same thing. Okay. Okay. Now, why did we need to construct P? So the thing is that P is the thing that, let's go, if what you mean is that, like, why do you need to construct P if all you care about is the diagonal matrix? P is important. P is the thing that diagonalizes the matrix A. And to go back to this thing that I had written here before, if you want to compute this A to the K, you need P. Right? You can't do it just with D to the K, because remember, A being diagonalizable does not mean that A is equal to D. Right? The matrix you start with, A, is certainly not a diagonal matrix typically. So you need the P because the P tells you how to change A to be the diagonal matrix. So in fact, I'm glad you asked that question, because there is a reason why we use the letter P here. Where did we use the letter P before? Let me read the other questions while I ask that. So where did we use the letter P in this way before? Okay, someone said, going back a second, you're saying that in this case, minus 2 had multiplicity 2, and we had a 2 vector basis. That would not necessarily be the case. That's right, Gustavo. That is not the case in general. And when we don't have that, then we're screwed. That's exactly what happens when you have a matrix that's not diagonalizable. That exact thing is what happens. So yes, so someone said, change of coordinates. That's exactly when we used the P before. And so what you can view this as is you are changing a basis, right? You are changing the basis of your vector space to a space where A is diagonal. Okay, so one way to view this, diagonalization is it is a change of basis to a basis where the matrix A is diagonal. Okay. All right. So this is an equivalent way of thinking about diagonalization. In fact, when you come across matrices that have been diagonalized, like in the literature, this is exactly what is said. So an example of this, like in my dissertation, I am dealing with a bunch of these 3x3 matrices. But when I want to deal with them, they're always diagonal. Now, they're not always diagonal. They're just a generic matrix. But the point is that they're nice enough, and so I can deal with them. I can deal with a matrix representative of those things, which is diagonal. And what is meant by that, the second you say the word, matrix representative, or a representative matrix in the same conjugacy class, what you're really saying is it's a diagonalizable matrix. It's similar to a diagonal matrix, and so you use the diagonal matrix instead. You consider changing your basis so that the matrix you're dealing with is diagonal. Okay, so question, what can go wrong? We've already gone over this a little bit. So the question is, what can go wrong? As someone else just asked, how do you know if it's diagonalizable? Let's look at an example here. So we have the matrix. I'm going to read row-wise. This is 2, 4, 3, minus 4, minus 6, minus 3, 3, 3, 1. Okay. It turns out that if you compute the characteristic polynomial, this actually has the exact same characteristic polynomial as the first example. So this is minus lambda cubed minus 3 lambda squared plus 4. So this is the exact same characteristic polynomial that we got before. Okay, so its eigenvalues are the same as our previous matrix. So eigenvalues are 1 and minus 2. The multiplicity of these eigenvalues is 1 and 2. Okay, so all that is the same as our first example. But we're going to see this matrix is not diagonalizable. Okay, in fact, if you look at the eigenspaces, so what is the lambda equals 1 eigenspace? So the lambda equals 1 eigenspace is, remember, this is the null space of A minus 1i. So this is the null space of A minus I. And it is one-dimensional, so its basis is V1, which is 1 minus 1, 1. And the lambda equals lambda equals minus 2 eigenspace. So this is the null space of A plus 2i. This has a basis consisting of a single basis vector. So its basis is minus 1, 1, 0. So if you write out, A plus 2i, so set up the equation A plus, 2iv is equal to 0 and solve for v, right, in parametric vector form, you see that you just get a single basis vector. It's one dimensional. Okay, if you compute the dimension of the null space, it's one dimensional. So there are no other eigenvalues. There's no other place to get my third linearly independent eigenvector. All right, so not possible to construct an eigenvector basis of R3. So A is not diagonalizable. Okay. And yes, so you would have to go through all of this in order to see that this is the case, unless you were given some additional info, right? So you can come up with contrived examples where you know what the dimension of certain eigenspaces are, and this can nail down whether or not the thing is diagonalizable. So there are some examples of this in the exercises. In fact, your next homework, which I'll assign sometime in the next couple days, will include problems like this, where I basically say, okay, suppose you have a matrix, and here's the size of the matrix, and suppose that here's its eigenvalues, here's the multiplicity of the eigenvalues, here's the dimensions of some of the eigenspaces. Is that enough to say whether or not A is diagonalizable? So you need some additional info. The point is clearly the eigenvalues of the matrix, the size of the matrix, the multiplicity of the eigenvalues is not enough info. Because this actually had the exact same eigenvalues and the exact same multiplicity and the same size as that previous example, right? But this was not, from that alone, you certainly can't tell. You got to actually write out and find the dimension of these null spaces, or these eigenspaces instead. Okay, and so what is one easy thing to say? Okay, so here's one thing that we can say. What if you have a matrix that has nothing but distinct eigenvalues, right? So, basically, what is kind of like the minimum amount of info that you could know? As I mentioned before, if you know that an eigenvalue is simple and it has multiplicity 1, then the dimension of the eigenspace has to actually be 1. We know the dimension of the eigenspace can't be 0, right? So the dimension of the eigenspace can never be 0. It has to always be at least 1. And so then the question is it, what is the largest it can be? The answer to that is going to come into my next theorem. And the answer to that is it's bounded above by the multiplicity of the eigenvalue. So it's bounded above by the multiplicity, and it's bounded below by 1. Okay. So what this means then is that an n by n matrix with n distinct eigenvalues is diagonalizable. Why? Basically, the idea here is if you have n distinct eigenvalues, each of the eigenspaces associated to those things has dimension 1. And so for each eigenvalue, you get one eigenvector. Those, because they come from different eigenspaces, are guaranteed to be linearly independent. Okay. And so you get n linearly independent eigenvectors, and you're done. Okay. It's diagonalizable by the diagonalization theorem. Okay. So this is a nice fact, and this is exactly what you're going to use many, many times. You have some given matrix. This is kind of the simplest or the least amount of info you could have. If you have distinct eigenvalues, you're automatically done. It's diagonalizable, and you're good to go. If the eigenvalues are not distinct, then it's more complicated. So question, what if... what if I have eigenvalues that are not distinct? Well, what this means, if you have eigenvalues that are not distinct, it means that you have repeated eigenvalues, right? You have eigenvalues that have multiplicity bigger than 1. Okay, so eigenvalues that are not just simple eigenvalues. Okay, someone's asking, they say random questions, only square matrices can be raised to the power. Okay, yeah, because you can't form the product in both ways, right? Yeah, so we're only going to be talking about square matrices for that. It doesn't matter too much to think about those things because like the determinant, for instance, only makes sense for square matrices anyway. So yeah, whenever you're talking about eigenvalues, anything to do with eigenvalues, you're always going to be dealing with the square matrix. Okay, so what if I have eigenvalues that are not distinct? So I have this big theorem that tells me exactly what it is that goes on, and this is the important thing that explains exactly what's happening. So let A be an n by n matrix whose distinct eigenvalues are listed. And whose distinct eigenvalues are, say, lambda 1 to lambda p. Okay? So there's 3 parts to this. So the first is for k between 1 and p, the dimension of the eigenspace for are associated to lambda sub k is less than or equal to the multiplicity of lambda sub k. So a quick way of writing that is the dimension of the null space of A minus lambda sub k I is less than or equal to the multiplicity of lambda sub k as a root of the characteristic polynomial. Okay. And Gustavo asks states the question of, so this dimension has to always equal the multiplicity. Yes, that's the idea. The idea is that you can't, this always has to be an equality if you want the thing to be diagonalizable. That's right. But unfortunately, in general, this is all you get. Now, this dimension is also, technically, right, this is also always bounded by 1. That's always true. But this is the thing that's important. And that's why when the multiplicity is equal to 1, this dimension is guaranteed to be 1 for each of those eigenvalues. Okay, so technically I always have a 1 bounding this dimension below. And that's why the second that your multiplicity eigenvalue is 1, the dimension associated eigenspace is always 1. Okay, so secondly, what's next? A is diagonalizable. So A is diagable if and only if so this is diagonalizable if and only if the sum of the dimensions of the eigenspace are equal to n. So if the sum of the dimensions of the eigenspace, or the eigenspaces, equals n, and this happens if and only if the characteristic polynomial factors completely into linear factors and the dimension of the eigenspace equals a multiplicity. Right, so, and this happens if and only if 1, the characteristic polynomial fully factors, when we say completely factors, we mean in terms of linear factors, and 2, the dimension of the eigenspaces are equal to the multiplicity of lambda sub k. So the dimension of the eigenspaces, for lambda sub k, are equal to the multiplicity of lambda sub k. Yeah, which is what we said. If that doesn't happen, you're out of luck. Okay. All right, and then lastly, if A is diagonalizable, so if A is diagonalizable and B sub k is a basis for the eigenspace corresponding to each of these things, so and script B sub k is a basis for the eigenspace of lambda sub k, that is the null space of A minus lambda sub ki, then the total collection of vectors from all those bases form an eigenvector basis for Rn. Then the vectors in the collection of all of these things up to B sub p, I should say, form an eigenvector basis for Rn. Okay. And so, again, this just totally tells you exactly what it is that's going on here. What's the most important thing is this inequality and the fact that if this process is going to work, these dimensions have to match up. So maybe I'll just restate that. So the big takeaway. So A is diagonalizable if and only if the dimension of the eigenspace associated to lambda sub k is equal to the multiplicity of lambda sub k for every eigenvalue. Okay. So this is the extra info that I mentioned. It is the dimension of the eigenspaces that matters. Okay. All right. This is the thing that tells you whether or not a matrix can be diagonalizable. Without this info, there's no way of telling you. You have to figure this out somehow. So otherwise, it's impossible to tell whether or not a matrix is diagonalizable. Now, one more thing. Suppose A is not diagonalizable. Well, what then? Right? Are we just totally screwed and we have no way of analyzing it in a similar fashion? Well, the answer is No, not totally. So we're not totally we're not totally done here. In fact, basically any matrix can be put into a form that, while it's not diagonalizable, it is we'll say close to being diagonalizable. So in many cases, there is still a form A can be put into in the same way that is convenient in a similar fashion to diagonalization. I'm not going to talk about it right now. Hopefully by the end of class I'll be able to mention it. This is the Jordan canonical form. So I'm not going to mention this right now, but this will be like one of the last things I talk about in the class. So, in fact, this form is so useful that when you do any kind of computations in abstract linear algebra, you basically just assume that the matrix you're working with is already put in this form. This form becomes the diagonalized form if the matrix is diagonalizable. If it's not, then it is put into a bunch of blocks that are nice. Okay, and that's all I'll say for now. Okay. All right. So that's that, and I think that's about all of the time I have for today. So we're almost done with everything we want to say about eigenvalues and eigenvectors. And so we will we will finish what's left of chapter 5, which is really just one more case, so that's complex eigenvalues. So I'll talk about complex eigenvalues next time, and mention, what basically a way to interpret what a matrix having complex eigenvalues means. And after that, we'll be moving on to chapter 6. So chapter 6 goes back to an abstract treatment of so things that you've seen before, but we're gonna go over them again, which is things like the inner product, dot product, and notions of vectors being orthogonal. So we will discuss those things in chapter 6, and hopefully in like another week and a half, basically we'll be done with the bulk of that, and what will be left then is tidying up chapter 7, and then that's pretty much the course. So we are headed into the home stretch here. So anyway, that's the plan. So I will post. Someone's asking in the chat for homework. I will post homework in the next couple days. You'll have about a week to do it. It will entirely concern eigenvalues and eigenvectors. Okay, that will be the total the total thing that is covered by the homework. So anyway, that is the plan. Just pay attention to announcements I make. So everything should be back to normal now. There shouldn't need to reschedule any lectures or anything like that. When there is going to be some supplemental lectures in the future, I'll let you know. Like I said, that's probably going to happen over Thanksgiving. So anyway, I will see you all on Friday. So we will finish. Like I said, we'll finish chapter 5 on Friday. Probably start on chapter 6.